Yeah.
And he must be knowing students and Professor Ranendra Ghosh.
Can you say that again? Last part.
No, he is asking whether you know our dean students.
I haven't. I don't think
Professor
the
Ranendra
course
Ghosh.
was.
Because before he joined, anyway, I think let us revitalize the connectivity with you and your friends and the alumni of DAIICT. Okay?
Yes, I'll be very happy to do that. Yeah, get in touch with. Yeah.
So who is going to start? Here, are you going to start?
Yes, so I will be starting.
Please start. We hijacked you.
So if you have enough audience, then you can start. No problem.
All right, we'll just.
Siddharth, are you from Ahmedabad?
I am originally from Bihar.
Okay. And do you have a plan to come to India to meet your parents anytime?
I usually visit like twice a year, but because of this pandemic, I have not been able to do that. I'm definitely planning to visit in this summer.
You know that when there is a disruption, there is a ray of hope. And the hope is that your original has started and you guys are giving lectures. That is a very, very positive trend, you know.
Yes.
Yes, here you can start. I don't want to disturb you. Please go ahead. And you can send me mail, Siddharth. You know my email address.
Yes.
And you can always, if you have some suggestions, some scope of improvement, I welcome your suggestions and comments. Okay.
Definitely, Yogesh Gupta. I'll be in touch with you.
All right. A very good evening and a warm welcome to the Alumni Lecture Session, Chapter 3. Student Body Government has taken up the initiative of hosting the Alumni Lecture Series. We have been inviting alumni who have achieved extraordinary feat in various fields, delivered talks, and encouraged their students to work hard. They have talked about their work and interacted with the community at the DAIICT. So far, we have completed 2 successful sessions. We hosted Mr. Mayank Mishra, a 2009 alumnus, in the first chapter, and Mr. Anirudh Das, another 2009 alumnus, in the second chapter. The year 2021 has brought new hope in everyone's life. It is easy to get carried away by all the new plans, but it is essential. Stay focused to achieve your academic goals. The third chapter of Alumni Lecture Series aims to help you do just that. Today, we have with us the Director, Dean students, and other faculty members of the Institute for this session, which also includes Professor Naresh Jotwani, under whom our guest, Siddharth Kumar, had undertaken his PhD project. Glad to have you here. Our Director, Dr. K.S. Das Gupta, has been very supportive and has always encouraged us to conduct such sessions. Sir, I will request you to say a few words.
Yes, a very good evening to my new friend Siddharth and all my colleagues and SPG team. And first, I welcome you back, Siddharth, to our institute. And I am really, really delighted that you have agreed to give a talk. And I believe that, in an institute like ours, alumni plays a very important role, which we cannot ignore and we should not ignore. So saying so, I take it very seriously that this sort of connectivity is very important and it should be a sustained connectivity. It should not be an impulse. So I wish that all of you who are, this institute is yours. You have to make sure that whoever has time, and we should create a calendar for 21, and maybe every 2 months or every 3 months we should be able to arrange the talk. More than that, I want your active participation in giving us some suggestions saying that what type of new program, if at all we want to introduce, because we have a lot of programs on our card. And also you should be able to interact with the students, because this is the new normal, and where the students are not in the campus, we ourselves are virtually connected. So they want moral support, they want certain, encouragement. So at that point, if the students like you and all Anirudh, Mayank and all your friends will be a great, a moral booster to the students. And we also think that there are a lot of electives which you people can float. And you know that these sort of electives like parallel I/O and data parallel deductive databases and high performance computing is excellent for the students of data science, students of machine learning, students of undergraduate program. And I'm happy to inform you, Siddharth, that Government of Gujarat has given Param Shevak, which is a supercomputer from CDAC. Of course, computer is not, it is a supercomputer, and we have a high performance computing center. So that way, we have facilities, we want to increase the facility, but I want your collaboration, cooperation very actively. And I wish that, you connect with us, connect with me directly, such that I can take your suggestions and try to see how it can be implemented. So I would like to discuss with you, all of you, in a different group, maybe every semester once, to understand and capture, because the perception of our institute is very, very important, as you know, in NIRF ranking. And you people are the top bearer of our institute. And every time they ask how many alumni are with you, how many alumni are being born. And since all of you are doing excellent job and excellent contributing to the US economy, you should be able to come and also contribute to Indian DAIICT intellectual competition. Okay. So I'm very delighted to have you on this, and but it is not a fire and forget that I see you once and I forget your face. You can keep on sending mail to me, and or you can send mail to Dean students or Suman Mitra or the new Dean academic program, Professor Maniklal Das, whom you may be knowing because he must have been there at that time. So with this, I want to create an ecosystem of alumni where alumni will suggest that I want to float this elective, and we should be able to do that, because the elective is basically a specialization and domain expertise. Sometimes getting faculty on that is very difficult. And we are trying to do an online degree program with Aggregation in a 2-year degree program. One is called M.Tech in computer science with specialization in data science, and another is MSc in data science. So definitely you can always give some lectures on that. So take it as your institute, it is your institute, and see that what way you can give a positive feedback, and which will help us, and it will also say that yes, you have contributed positively intellectually to our institute. So Siddharth, all the best. Look forward to see you more often, if not physically, but virtually. So all the best, Siddharth. You can continue. And I'm sorry I have to go somewhere that has some personal work. I will not be able to attend your lecture, but it will be my pleasure to have more detailed chat with you. Thank you, Siddharth. All the best.
Thank you, sir. Professor Arindu Ghosh, the Dean, has always been very supportive to the student body government. His motivation and dedicated involvement in the activities for the welfare of the student community has always been a pillar of strength for the body government. I'd like to request him to say a few words as well.
Am I audible? Am I audible?
Perfectly, yes.
Yes, sir.
Okay. Thank you, Bahira. Siddharth, we don't know each other. but your best identity is that you are alumni of DAIICT. It doesn't matter whether you are Siddharth or you are somebody else. And we are delighted to have you today in this alumni lecture series. We are already having 2 lectures by Mayank and Anirudh, and you are the third one. And I'm sure the students are enjoying this lecture series, and they are waiting for this lecture series. And I'm sure they will be enjoying it. And there will be a lot of queries also out of it. Only try to ensure that the students are, yes, that getting certain information which they're looking at you with your kind of a topic you have decided. That's kind of an information. Maybe if it is possible to give it in a very concise manner, it will be more enjoyable. So Siddharth, you are welcome once more, and I hope this your interaction will be long lasting. And I will request you to also ensure that you know someone who are our alumni and would be like to come forward for this kind of alumni lecture series. Please let me know. We'll be in touch with them, and then probably we'll arrange a alumni lecture series again. Thank you, Siddharth. Thank you. Please carry on. Thank you.
Thank you.
Thank you, sir. To take ahead the alumni lecture series, we have a very special guest today. From being a student at DAIICT, doing his PhD from University of Utah, to becoming an assistant professor at University of Alabama, he has come a long way. Our guest for tonight, Mr. Siddharth Kumar, is here to tell us all about his journey and all his milestones. Siddharth Kumar has developed scalable algorithms for high-performance data movement that can facilitate key requirements of data management, which includes parallel input-output, out-of-course processing, streaming, and paging. With his research in high-performance computing and large-scale data management, he has not only received the Best Paper Award for Distributed Relational Algebra at Scale at HiPC 2019, but also won the Hans Meuer Best Research Paper Award for Load Balancing Parallel Relational Algebra at International Supercomputing Conference in 2020. Though these are some great milestones of his life, I'm pretty sure this is just the iceberg tip. In today's talk, he will present the first parallel framework for high-performance moment of analysis and visualization appropriate multi-resolution data, and will also present a HPC framework for scalable relational algebra that forms a basis of primitive operations. Let's get started with it. The stage, it's all yours, sir.
Hi, is my voice loud and clear?
Yes.
Yes, Siddharth.
All right. Okay. Thank you here. Thank you, Dr. Mitra, Dr. Ghosh, Dr. Dasgupta. This is an absolute honor for me. I have such fond memories of DAIICT and so much of gratitude towards DAIICT. The technical foundation that DAIICT helped me, and I'll be eternally grateful for that. So let's move on with the talk. So this is a brief outline of my talk. I'm going to start by the time spent at DAIICT and my professional journey. Then going to talk about HPC trends, and then 2 niche areas that I do research in: parallel I/O and data parallel relational algebra. So let's start with time at DAIICT. All right, so this is my professional journey. I joined DAIICT in 2005, spent 4 years, and 2009 I decided to go for a master's at the University of Utah, which eventually turned into a PhD and then to a postdoc. Spent roughly around 9 years at University of Utah, and at the end of that, I realized that I really enjoy working in the area of research, being able to do the things that I really want and I really like. So decided to move on to University of Alabama as an assistant professor, where I'm currently working at. So I want to now talk about each of these phases and how I transitioned from my bachelor's to PhD and then to the assistant professor position. So it all started in 2007, I would say, where I started become very interested in computer graphics. And back then there weren't a lot of online resources, so I turned my back at the resource center, the amazing resource center that we have at DAIICT, and there's so many nice books there. And I found a book on graphics, and like many of us, I googled the author of the book, Peter Shirley. He happened to be a professor at the University of Utah back then, and he is a real pioneer in the field of computer graphics. Digging a bit more into this, the University of Utah is actually one of the forefront universities in the field of graphics. It's actually one of the places where graphics started, the famous Utah teapot. Um, and if you look at famous University of Utah alumni, then Ed Catmull name shows up. And Ed Catmull is a Turing Award, Academy Award winner, and he runs Disney Pixar. So I was really excited to apply to University of Utah, and thanks to a decent profile that I had at DAIICT and letters of recommendation that I got from the professors at DAIICT, I did get an admit at University of Utah, and where I went to learn and study graphics. But it's quite interesting that University of Utah doesn't really do a whole lot of direct graphics. It does a lot of applied computer graphics, which is awesome. Using ideas of graphics to visualize and understand large volumes of data, scientific visualization, scientific computing, image processing, signal processing, these kind of things. And I got very interested in that as well. And like many of us, I wanted to get funding, wanted to do some research, and luckily I got to work with Professor Valerio Pascucci, and he became my advisor, my master's advisor, and started to work with him. And the institute at University of Utah was called a SKI Institute, the Scientific Computing and Imaging Institute. And while working there, I got an opportunity to intern at Argonne National Laboratory, and that's where I started to work on high performance computing, where the HPC bug kind of bit me. Like I started to really enjoy working on really large problems, being able to scale problems on supercomputers. I got to work on the Mira supercomputer, which was a really fast machine back then, and really enjoying the process. And by the end of my summer, I was convinced that I want to do a PhD and keep doing this more. And that's how I transitioned from DAIICT to doing a PhD at the University of Utah, and stayed there for 9 years with lots of ups and downs, and which eventually culminated into me joining the University of Alabama at Birmingham as an assistant professor. So now, before I move forward, I would like to take back and talk a bit about my time at DAIICT and how it was like back then. So I would just like to say a few things. What DAIICT managed to do was it instilled a sense of confidence, uh, and a confidence backed by knowledge, and that was the key part. I really felt like I could stand on my own. I could write really good code. I can talk computer science. And that was a very, very good feeling. And I remember many incidents at DICT. It was in the very first semester, Dr. Mathuria was teaching us computer system organization. And it was a tough course, and I did not get really good grades, but I learned so much from that course. I remember when he was teaching about multiplexers, decoders, I felt like, oh, I can use all of this to actually build my own calculator. And that was a very empowering feeling. And throughout the time at DICT, I had many of those moments where I was like, yes, this is really, really cool. And I really like this. I remember a guest lecture by Professor Gautam Datta, where he was talking about quantum physics, and it was a 1 hour lecture in a course that Dr. Adinath Sarkar was teaching, and that lecture was really, really good. It was really inspiring. Um, Many more incidents of this sort, and all of this and support from faculty members. It was all throughout the stay at DICT. So my interest in graphics and kind of culminated into me choosing a B.Tech project in that area. And I got the opportunity to be mentored by Dr. Jotwani and Dr. Datta for my B.Tech project. And that was really, really a nice experience, I would say. And it's almost a cathartic experience for me to be able to talk about my B.Tech project again. Like, I feel like I probably did not do a very good job explaining my BTP project when I was doing that 11 years ago. So here I'll be talking about it for like 2 minutes. So this is what I developed, and I'm still very proud of this. I and my friend Aditya Prakash, we developed this Air for Human Simulator. We used to call it AFHS. It's basically a rendering of the part of the human anatomy that gets in touch with the air that we breathe in. And that is basically the cardiorespiratory system, the human heart and the lungs. So these are the models that we developed, and this is a screenshot of the system that I and my friend Aditya developed during the B.Tech project. So this is the a rendering of the system. It had a graphic canvas where you could play with 3D models, and the graph area where you could see how different organs were changing shape. I didn't know back then, but it was actually like some variant of the EKG that you have. This graph area showed that. So this is an example of an alveoli. This is and you could move this, play with this. So this is, I don't have the actual videos for this, but this is some screenshots of that. And I remember Dr. Datta really encouraged us to go beyond graphics and go into the physics of all these systems. So we actually also simulated how two different containers with different pressure, when interacting with each other, would reach a state of equilibrium. And we modeled that as part of the system. And this is the lungs. More of that. The human heart. We use learned Maya to create these 3D object files and imported this into our system. So yeah, so this is something that I'm still very proud of, the B.Tech project that I did at DAIICT, and it kind of gave me some more confidence, because this was a lot of code that I had to write, and the more code you write, the better you feel, the more confident you get. So this is the screenshot, and this is an old photo that I have with Professor Gautam Datta. And another incident, a major defining moment for me was when I was working with Dr. Jotwani, and I was doing some small project with him, and it was a project on this adjoining nice simulator that Dr. Jotwani was working on with his book. And that was a very rewarding experience, making some contribution to something tangible, something real. And at the end of my work with Dr. Jotwani, I went to meet him, and then he said that, oh yeah, the book is out, and he casually mentioned that I've added your name in the preface of the book, and you can see here is my name, Sidharth Kumar. I've worked hard on the Assembler simulator for NICE, and this was such a amazing moment for me. And in hindsight, I feel like this was actually a moment where it made me feel like I want to keep doing something like this. I want to be able to publish more. I want to be able to get into research. And it was one of the more special moments of my stay at DAIICT, I would say. All right, so now I'll move on to the next part of my talk. So, So before that, so another aspect that DAIICT kind of is very visibly important. This is my CV after a year at University of Utah, and if you look at the major projects, then 4 of the 6 projects that I had still from DAIICT. And all of these are really good projects that I got to work on. And they were, again, like instrumental in helping me move forward. So again, like the importance of the curriculum and the importance of the core difficult courses that one encounters at the DAIICT. Just wanted to show you all of that. All right, so let's move on to the next topic. This is HPC Trends. I'm sure all of you know what high performance computing is. So this is more of a textbook definition. High performance computing most generally refers to the practice of aggregating compute powers in a way that delivers much higher performance than one could get out of a typical desktop computer or workstation in order to solve large problems in science, engineering, or business. So major part of HPC are supercomputers. So this is a screenshot of the Theta supercomputer, which is at Argonne National Lab, and I've worked very closely with this machine. I have a bunch of projects that I'm going to be talking about today that are deployed on the Theta supercomputer. This is the Pratyush supercomputer, is the fastest supercomputer in India. And you don't really have to have a supercomputer. You can actually build your own. And this is a mini cluster developed out of Raspberry Pis. And you can make this in $100. And it can also run parallel program on this mini cluster of yours. And HPC is starting to become very mainstream. A lot of big companies are investing in HPC and having cloud support, which has HPC backend. So this is AWS supporting Elastic HPC cluster. This is Microsoft Azure supporting HPC environment. And just, I thought I'll have some slide on what exactly people do with high performance computing. And the answer is a lot of stuff. So machine learning and deep learning and neural networks, these are all taking advantage of high performance computing, graphic processing units, tensor processing unit, and multi-core architecture. These are all key areas of research these days. More traditional work is computational fluid dynamics. Computational fluid dynamics is a branch of fluid mechanics that uses numerical analysis and data structure to analyze and solve problems that involve fluid flow. CFDs apply to a wide range of research: aerodynamics, environmental engineering, weather simulation, biological engineering, and a lot of other area. So climate modeling is also something that is done extensively on high performance computing platforms. So this is a screenshot of climate modeling, some stuff about that. Molecular dynamics is also something that is heavily done on HPC machines. Molecular dynamics is a computer simulation method for analyzing the physical movement of atoms and molecules. So this is something that is also done a lot on HPC machines. This is graph mining. So graphs occur everywhere, social networks. How do you mine graph? How do you extract information from graph? So this is an example of a graph mining project: Exagraph, parallel partitioning and coloring of exascale applications done on HPC machines. In short, HPC would be everywhere very soon, if not already. HPC would be prominent in bioinformatics, mathematics, CFD, deep learning, geophysics, astrophysics, weather modeling databases, and it's coming up in more niche areas such as static analysis, precision medicine, cryptography, quantum computing. And I just have a slide on the fastest supercomputer, and I thought I'll talk about that. This is the Fugaku supercomputer at Japan, and it is at Riken. And it boasts of approximately 7.3 million compute cores and 415.5 petaflops. That is 10 to the power of 15 floating point operations per second. That's a lot of compute capability. These machines typically are used for drug discovery, personalized medicine, weather and climate modeling, clean energy development, and many other areas. So I thought I'll have a slide on the specs on 2 of the fastest supercomputers. So this is the Tihane 2 supercomputer, and the Mira supercomputer at Argonne National Lab. So these are some of the specs of the machine. So the theoretical peak of DA-IICT is 55 petaflops per second, and for Mira it's 10 petaflop per second. Look at the number of compute cores. On DA-IICT it's 3 million, on Mira it's close to 1 million. The processor on the DA-IICT is Intel Xeon. On Mira it's Power. It's IBM's Power BQC, and so this is just to give you a sense of the scale of these machines. And how do you typically get how do you typically track these machines? How big these are? There's a nice website, top500.org, which maintains a list of all the fast supercomputers, and they have a lot of infographics on this. You can see China is typically leading in the race of supercomputers, which has the maximum number of machines out there in the 500 fastest list. And this is a graph that shows the speed of the fastest supercomputer. So if you look at the black curve, this is basically how the speed of the fastest supercomputer has been changing right from 1993 all the way to 2013. And you can get more recent graphs if you look at the website, the top 500. But this should give you a sense of how dynamic and fast this landscape of HPC is. If you actually look at this trend, so the orange trend line corresponds to the 500th fastest supercomputer. It only takes around 6 to 8 years for the fastest supercomputer to become the 500th fastest supercomputer. This again kind of gives you a sense of how fast this field is evolving and changing. Let's look at the list of the 10 fastest supercomputers. A bunch of questions that you ask. How do you program when you have million cores? If you look at the number of cores. Other thing to note is the power. And that's kind of an important thing, because you don't want to just keep building these machines by stacking more compute cores. You want to be able to build these machines in a power efficient manner. And that's kind of a very, very hard constraint that's being added, because it's important to be able to have a machine that does not end up consuming more than what it is useful for. Other thing to note is the machines here, they are not only just pure CPUs, but they usually have some kind of accelerators, GPUs associated with these machines. On every node, there is a lot of computation because of GPUs. And so that's also a kind of a difficult avenue. How do you program a GPU effectively, and especially in HPC environment? So just hands-on, how do you build a supercomputer? So you take a bunch of a CPU, add some memory and some I/O. You put multiple CPUs on a board. You stack a bunch of these boards in a rack. You have a warehouse with these cabinets, and you wire up a network. So this is a very, very hand-wavy explanation of what a supercomputer looks like. So the thing that makes this very efficient is the high-speed interconnect, the InfiniBand technology that lets you have very low latency when you have to move data from one compute core to the other. It kind of helps you have this big machine which works in a lockstep manner. It almost feels like you are working on just one machine. And how do you actually code these big supercomputers? The core programming paradigm used is MPI, which is message passing interface. And there are three high-level protocols of communication. One is point-to-point, the other is one-sided, and the other is collective. So MPI is the most important thing associated with parallel programming. All right, so now let me talk about the trends that we are seeing moving forward, the two things that I want to talk about in this graph. So look at the x-axis. This is 2009 and 2018. The primary y-axis, this is the compute peak of the fastest supercomputer. So in 2009, the fastest supercomputer was 1.5 petaflops per second. 2018, it is around 100 petaflops per second. Almost 100 times improvement in speed. Now that itself is a huge thing. Applications, programs that are running on these machines need to be able to scale to these fast supercomputers, to these fast machines as we move forward. So this is one key trend. The other trend is with respect to the enormous amount of data that is being generated and how do you actually handle that. So this green line corresponds to the speed of the I/O systems. How do you move the data effectively from the compute systems to the storage system? And if you look at the speed of this, it used to be 0.2 terabytes per second, and it's around half terabytes per second in 2018. So this is not growing at the same pace at which the compute speed is growing. Now, this actually is a very, very important thing to note. This kind of creates an imbalance in the entire HPC system. The rate at which you are producing the data is much faster than the rate at which you can move the data. And that is an important trend. So there is this widening gap between I/O speed and the compute speed. So just to make this clear, what do I mean by compute speeds? Compute speed is the part where you run things on the supercomputer, and the I/O speed is the part where you move the data from the compute clusters, the compute nodes, to the HPC system. So this is typical pipeline of how things work in an HPC environment. You have simulations running on supercomputers, data being generated, and then data being analyzed and visualized. So now let me delve into the areas that I do research in. Parallel I/O. So I have a couple of figures to show how things have changed. So 2005, this used to be 128 megabytes. 2014, this is 128 gigabytes. This is a screenshot that I took yesterday of the traffic that you have on the web. So internet users in the world, total number of websites. This again kind of gives you a sense of the scale that we have. And now let me go back to the HPC pipeline that I was talking about. So this is an example of some of the simulations that are run on an HPC environment. For example, this is Riley-Taylor's instability simulation, where you study how two different fluids of different density, when they interact, then what happens. And at the bottom is a huge boiler simulation. And these are run on these big machines, which generate enormous amounts of data. And two challenges are there. How do you actually deal with this large volume of data when it is being generated from these simulations? How do you move this data effectively from the compute cores to the storage system? You solve this problem. The next problem is, now what do you do with this data? You have more than hundreds of terabytes of data sitting. How do you actually use your compute system, your analysis system, to actually make inference from this data? And that's another big problem. So summarizing what I just told you, so parallel I/O is the part where you move the data from the compute system to the storage, and then you read the data to process the data for exploration. And analysis could be of statistics, topology, geometry, mining, or visualization. All right, so you might ask, like, this is both of these, parallel I/O and the out-of-core processing, they are some like two different facets of input-output. This is write and this is read. So what is the difference between these two? So the difference is because here, when you're writing the data, then you are actually using this big supercomputer. You are actually moving the data, which is distributed across million cores, and moving to a storage system. But when you're reading the data, you don't have a supercomputer reading the data. The kind of access that you are going to need for the task that you are going to indulge in with your analysis and visualization will not really be something that would be done at that scale. The analysis that you will be doing, you would be using a smaller cluster, and the analysis is usually something that you want to do in more of a real time. So something where latency is an important thing. You want quick feedback. You want to be able to visualize the data in a real-time environment. So something where you want to be able to access the data at multiple levels of resolution, or being able to just read a small chunk of the data. So the write part is more bandwidth bound, where you want to be able to write the data fast because you don't want to stall your simulation that is running on the supercomputer. On the read side, you want to make this fast, latency optimized reads. So these are kind of two different flavors of I/O operation. So this is what typically people would do. You have an I/O system that moves the data from the simulation system center to the storage system, and then you do some kind of processing on the data, and then the data becomes useful for analysis and visualization. Now, there is a lot of problem with this pipeline. One is there is an expensive processing phase where you have to convert the data from this initial format to a format which is more suitable for analysis and visualization, which is easier to read. And the other problem is that typically the I/O system also does not scale. Now, these are the two areas that my research fits in, tries to solve this problem. So what I've developed is an I/O system. It's called PIDX, which enables simulations to write data in a format which is inherently more suitable for analysis and visualization, which can be queried in a very, very effective manner. So it transforms the data on the fly to a format which is more suitable for analysis and visualization. So there is no processing overhead, and the I/O system is also very scalable. So the I/O problem is also solved, and thanks to the format, you can actually read the data in a very effective manner. So this is an example of a simulation that I was very closely associated with. This is a simulation that ran on the Argonne National Labs Mira supercomputer at 260,000 compute cores, generated 300 terabytes of data, lot of data. And this is a visualization of the final data that was generated out of it. So this is basically a huge coal boiler, and then you have combustible gases being poured into it, and then you want to study how this combustion happens. These are other projects that I was associated with. This is another combustion simulation data, and this is CAF simulation. This is at Saudi Arabia, KAUST. This is basically interacting with really large volumes of data in a very, very fast and an efficient manner. So again, this is visualizing large volumes of data in a very fast and efficient manner. And I want to kind of go a little bit into the technical details. Like, how do you actually access and interact with these large volumes of data in a very, very efficient manner with such low latency, and talk about that. So this is a very, very simple example of a 3D data set. So this is, just think of this as an image in 3D volumetric data, and how do you actually store this on the disk? So the most naive way would be row order. You take every slab, and then you basically take every row of that slab and you write it out. So this is how typically one does something like this. When you have the data in your application domain and how you translate into the file domain. So this is for a 2D image. Now, these are some other ways of doing it. So if you look at this scheme, this is called a Z-order scheme. This is based on the Hilbert curve. And the advantage of using something like a Z-order curve is that it preserves the spatial locality in more than just one dimension. So if you look at this row order scheme, then the spatial locality is preserved in only the row dimension. In column order, the spatial locality is preserved in the column dimension. Here, it is preserved in both dimension. What does this mean? It means that data, an image, which exists in 2D, also exists in 2D on the file. File is one-dimensional. So here you are actually translating the two-dimensional idea onto the file. So that is a cool insight. Another variant of the z-order curve is called as the hierarchical z-order curve, and that is what I have worked on. Here, not only you do have these z-order curves, but you also have a sense of hierarchy. And let me talk about this format in more detail. So look at this example. So at the top is the traditional row order data. Now, if you access row order data, then when you access a small chunk of the file, then you get a small region in the of the data. But here at the bottom, the data is actually stored using this hierarchical z-order scheme. Now, what this means is that when you access a small chunk of the file, then you actually get an approximate resolution of the data. If you access more, then you actually get a more finer refinement, finer approximate version of the actual data. And you can already get a sense of how important this could be when you're actually dealing with really large volumes of data, a data which is maybe a terabyte in size. But if you have the data organized in this format, then even if you're reading a small chunk of the data, you will still get an approximation of what exactly are you dealing with. And that is very key. So here, for example, if this is the data, and if you access a low resolution version of this, then you have to have this interleaved access when you are dealing with this row order data. But if you are dealing with this hierarchical z order, then you only have to access just the first few blocks of the file, and that will give you a lower resolution version of the actual image. How do you actually build something like this? So this is an example of that. So you take every sample, every other sample, and that is your the lowest resolution of your resolution pyramid, and then you work with every other sample, and then you do the same thing. You take every other sample in the other direction, and you keep on doing this. And this is how you actually develop something like this, a resolution pyramid. And there are many variations of this, and it depends on the application and the machine that you're working on. So this is a foray into the very core details of the format of the data. So this is another example, application layout and the read-friendly layout that I just showed you, the HG scheme. Now, how do you actually do this? So you create these hierarchies, and then you write it to a file. So as I was telling you this, so the data is written in this hierarchical z-order format, this multi-resolution format. Now, the challenge is to write this multi-resolution format in parallel in an HPC environment when the data is actually distributed across 1 million compute cores. And then you have to coordinate access and write to this hierarchical z-order format. And that is where the real challenge is. And that is what I did during my PhD. So data stored across these compute resources, and how do you actually move the data efficiently to the storage system and write it in this hierarchical z-order format. So challenges at the format level, challenges at the computer network level, and at the file system level. These are some of the low-level issues. I'm not going to go into a lot of details, but I do want to talk about the high-level ideas as to how you tackle a problem like this. So this is an example of how things would be in an HPC environment when the data is actually distributed across multiple compute cores. So here you have the data split across 4 machines, and this is the same data in the HZ format. And here I'm only showing you the final resolution level, and you can do the same thing for the other resolution levels as well. And the first step is the indexing, when you convert the data in the row order to this HZ order, and then you write it to a file. And you can see these kind of maps well. So you can actually do this indexing, this conversion of this row order application layout to this HZ order layout. in parallel across these machines and then write it to a file. Now, this becomes a challenge when you actually deal with dataset which do not map very well to the memory. So, for example, if you have a data which is non-power of 2 in dimension, this is a 6 by 6 data set. And here we had a 4 by 4 dimension data set. So when you have a 6 by 6, which is not a power of 2, things become a bit complicated because this resolution scheme is inherently dependent on the power of 2 level of details. Because you have to kind of divide the domain into half and half and half. So in a situation like this, you get this very ugly looking layout. And you can, as you can imagine, with this non-contiguous interleaved accesses, you're going to have really bad memory access, disk access, and all kinds of non-uniform, non-contiguous accesses are bad. So how do you solve this problem? So you basically invoke something called as regridding. So you have extra data communication and you reorganize the grid. For example, here you impose a power of 2 dimension box on this data, you move some data around, and now after this phase, you get this power of 2 dimension data set on every process. And if you look at the indexing on this, then you can see that the accesses are now more uniform. There are some holes, but there isn't this broken discontiguous access anymore. And that is kind of really, really key here. So this is an example of one of the innovations that I had to do in order to be able to facilitate an IO system for this multi-resolution scheme. And this is something that I published at Supercomputing 12, and I'm just seeing a question that how do you evaluate these two different schemes? And this is an example of how I actually evaluate. You actually count the number of packets. For example, on the left-hand side, it's the number of packets that you would have to have when you're dealing with non-power of 2 dimension data set. And you can see that the number of packets are enormous and the packet size is really small. But when you go with this restructured layout, then you see that the number of packets are less and the packet sizes are really big as well. So this shift from lots of small size packets of data to fewer large size packets. So when I say packets, I mean these interleaved data sizes. So here, for example, you have 2 packets on this green process. After this, you just have 1. So other problems was how do you actually write it out? Now, this was also a big concern because if you actually look at the full system, if you look at these different resolution levels and how you actually write it to a file, then every process is making a small access to the file when they're writing these resolution levels. So the file is actually going to have this global resolution view, right? So this region of the file is going to be written by 4 processes. Again by 4 process, again by 4 process. So you can see at the first file, a lot of processes are accessing. Now this is also not a good thing because when you have multiple processes accessing a file, then you get what is called as file locking contention. And you want to prevent that. You don't want to have synchronization costs. You don't want to have serialization costs when you're writing to a file, especially in an HPC environment. And that's how I did this next step in my research. Added this extra aggregation system, a 2-phase IO system, where instead of all the processes writing the data to a file, they buffered the data. So they move the data to an aggregation buffer. So these are the 2 buffers. And then the aggregator processes, which create these buffers, they go ahead and write the data out. So this was, again, very, very important to get a really scalable system. So this kind of gives you an idea of what kind of innovation that you have to have when you're dealing with a problem in an HPC environment. So I'm not going to talk about all the optimizations, but we did optimizations to reduce the communication cost as well. And after all the optimizations and all the innovations, we're able to have a system which actually scaled all the way to 768,000 compute cores. So x-axis is the number of cores, y-axis is the throughput in gigabytes per second of actual parallel I/O throughput. And here at this scale, I'm writing 6 terabytes of data every time step, and I was able to extract 80% of the theoretical peak bandwidth on this machine, which is a pretty impressive number. And thanks to the format, the nature of the format, you were able to visualize the data very effectively in a very, very interactive, low latency manner. And this is a visualization of terabytes of data. And other aspects to this is how do you deal with these problems from a different perspective? Like, is there a way to actually store the data in a more adaptive manner? So this is another paper that I wrote where I created this adaptive storage system and an I/O system where instead of writing the entire data at full resolution, you identify regions of the data which is of importance and you write them at high resolution and the others at low resolution. So this also kind of helps you save on time, and the overall storage footprint also goes down. So instead of 16 gigabytes, this takes only 4 gigabytes. Instead of taking 16 seconds, this takes only 6 seconds. The same idea could be used for datasets which are inherently adaptive in resolution. The other aspect is being able to tune these systems, being able to extract maximum bandwidth out of these systems. And that's where I relied on machine learning, where we did this characterization of the environment, the entire machine, and got some training data and created performance model out of it, and then use it for performance prediction. So this is the pipeline, and this is give you a sense of the tunable parameters that we were dealing with: the number of aggregators, the number of files, whether we are using restructuring, what is the amount of data every process has, and the output of this was the actual throughput, the bandwidth that you would get. There's a bunch of machine learning models we tried, and the model did perform well, and we were actually able to use the machine learning system to tune the system to be able to identify what kind of parameters we need to have in order to attain maximum bandwidth out of the system. This is a paper that published at the Supercomputing conference in 2013. Some of the machines that I was fortunate to deploy my system on and get really impressive throughput numbers. I think this is the list of the papers till 2017. So till now I was talking about this problem of dealing with large volumes of data, of parallel I/O. How do you actually leverage a supercomputer to write data in a format which is more suitable for analysis and visualization? Now I'm going to shift gears, and this is something that I'm more doing these days. This is parallel relational algebra, and this is more of an application. How do you actually build an application on a supercomputer? And this application also generates lots and lots of data, and which is another challenge. But here I'm going to focus on more of engineering aspects, more of the research aspect in developing a scalable system rather than scalable data system. So before I get into a lot of details, so what is relational algebra? And I'm sure most of you are aware of this. This is basically core of databases. So it's a family of algebra with a well-founded semantics used for modeling the data stored in relational databases. Examples of array operations are selection, union, intersection, projections, and natural joins. So relation, for example, is this table, and then you have attributes, which is columns, and then tuples, which are rows. Selection is being able to select rows based on certain conditions. So selecting all the rows for age is greater than 34, when age is equal to weight. Then union, intersection, these are set operations. Cartesian product, all familiar with this. Natural join. This is kind of interesting, where you combine two tables based on a matching column. So for example, here we are combining these two tables based on the username. So you can see Sam P and Sam P matches. So we have this row in the new table, and then Sam P matches again. So we have that. Now we'll have 3 matches corresponding to Lee. So this is a natural join between these two tables. So this is just a quick introduction into what is array and examples of that. So projection is also when you project out a column. So for example, here, this is projecting out everything but the email and IP address from the input relational database. So where am I heading towards? So I'm heading towards developing a data parallel data log. So what is data log? So data log is a declarative logic programming language that is syntactically a subset of Prolog. It is often used as a query language for directive database. And data log recently has found a lot of applications in information extraction, program analysis, machine learning, cloud computing, security. So at a very high level, so you can write very optimized queries which can help extract more information from an existing database. A very simple example would be if you have a database for a graph. For example, this is an input graph G. These are all the edges that you have. Now you can write, example of a deductive example of a data. I have slides in the wrong order. So here, this is an example of a data log rule to extract all the paths from a given graph. So let me go into this a bit of detail. So here the first rule is saying that if you have an edge from X to Y, then you have a path to X to Y. So G is the input graph and T is the transitive closure, which computes all the paths of a given graph. So this is the first rule. The second rule is if there is a path from X to Y and there is an edge from Y to Z, then there is a path from X to Z. So with just these 2 lines of code, you will be able to compute all the paths in a graph. So this is an example of a simple data log program. Now, so this is basically you extracting more information from a given graph, given database. And how does this work? So why is this linked with relational algebra? Now, data log naturally compiles to relational algebra. Bunch of joins, bunch of unions and projections, which are done in a fixed point iteration. And an example of that with this same thing is here. So here you have the input graph, and then you apply the rules that I had in the last slide in a fixed point iteration, and then you add new paths. So here in the first iteration, you add these new paths of length 1. The next iteration, you add this new path of length 2. So for example, 0 to 4 is of length 2 because there is 0 to 1 and then 1 to 4. And you keep on doing that till you find all the paths or you reach a fixed point. So this is an example of a data log program being executed from the very beginning till the point it reaches the fixed point. So where does HPC come in? So HPC comes in where we are actually trying to take these array operations, these joins, these projections and unions, and scaling them up, have a parallel implementation of these array operations. And because of that, you'll be able to scale any application that you write on using data log on these big supercomputers. So relational algebra implemented on a supercomputer will let you solve really compute intensive problems on an HPC environment. And this has a lot of applications in deductive databases, applications in graph mining, program analysis. So deductive database could be as simple as extracting new derived tables from existing database with customers, inventories, and invoices, and write data log queries to identify high value users, identify shortages. In graph mining, which is a very, very popular field where you extract features from graph, it could be as simple as extracting the total number of triangles that you have in a graph, or extracting clicks, or finding paths, and finding symmetric edges. So these all can be written very succinctly using data log queries. And these data log queries will get compiled to array primitive operations, which again can be run on a HPC environment, because these array operations are have scalable implementations, and that's what this area of research is all about. So with this, you can have a framework that you can build graph mining applications, static analysis applications, and reactive databases on top of parallel relational algebra. And the key components of devising any HPC application is how do you actually distribute the load? So data partitioning, and then the computation part, and then the communication part, because in the end, you're solving one big problem, right? And then you have to partition it across these HPC compute cores. And then you have to solve the problems locally. And then you have to have some kind of communication to get the final global solution. That's why the communication is important. And I'm not going to go into a lot of detail with this, but I want to show you an example. So this is a graph, and this is the same transitive closure computation on this graph. So how do you partition? So you partition it across the join column. So this is an example of partitioning this graph across bunch of buckets and sub buckets, which is based on hashing on the join column. And so this is just an example of how you partition this data. And then the buckets are going to be distributed across these compute cores. And you can do this in a round robin manner. And this is an example of the entire flow of the system without going into a lot of detail. So this is just showing the high level overview. So you'll have to have intra-bucket communication just to distribute these data across these compute cores. And then you'll have the local join where these tables are going to be joined locally within every compute cores, and then you get new data out of these local operations, which needs to be transmitted to all the appropriate processes. So again, you'll have to have a communication phase, and then the local insert phase, that is inserting the new tuples that you have just received back in your tables, and doing the same thing again and again. So this goes back to the fixed point thing, where you keep on doing the same task till you reach a fixed point. So there are other challenges. How do you deal with imbalances when you have imbalanced data? So for example, spatial imbalance and temporal imbalance. So spatial imbalance occurs when you have a lot of tuples getting mapped to the same process. For example, here, if you look at the transitive closure of the graph here on the left side, then you can see that a lot of tuples, A, D, A, E, A, F, A, G, will be mapped to the same process. Now, this is again not a good thing, because this will create imbalance in the system, and load balancing is a big problem in an HPC environment. And you want to have systems which does not have that, because you don't want a process to be working more than others. And the other problem is temporal imbalance, and I'll show you an example of this. For example, this is an input graph. So this is the first step of the fixed point. You will get the new paths of length 1, and the next step, you will get W squared. So this is the width. So these are the new set of edges that you will get in the next iteration. And you can see that there is a explosion in the number of edges that you get in this iteration. And this will also create a lot of issues in terms of balance of the system. So we want to be able to handle these imbalances. So solving spatial imbalance. So we added this idea of dynamic load balancing, where during this the step, we added this idea of spatial load balancing, where we redistribute these sub buckets across processes so that the load is balanced. And bucket refinement and bucket consolidation are the steps that we use for this. And this temporal imbalance is something that we solve by thresholding. So instead of having these large amount of tuples being generated, we kind of threshold this. We do not let the system generate many tuples at once. We stop before it reaches a particular threshold, and this again leads to iteration rollover, because you'll have to process more number of iterations uh, if you hit the threshold. And this is a flow chart for that. And we scale this on the HPC supercomputer Theta. And these are some of the graphs that we use for this particular experiment. And this is some of the scaling results. So this is parallel join between tables. This is showing you how the machine works for this point of application at different scales. So starting with 64 cores, going all the way to 60,000 cores. And you can see that the system scales pretty well all the way till 4,000 compute cores. And after that, the scalability is not that great. And that is because of the communication cost that you have to have. Communications does start to become a bottleneck as you go at really high compute cores. You need to have really large problems to be able to have a scalable compute system at high scales. And this is a result that I'm really proud of. So this is the transcript closure of a graph generating billions of edges, billions of paths, and something that we ran on 32,000 compute cores. So yeah, so this is all about research, and I would like to conclude my talk. And I hope you got a sense of the kind of problems that I work on, some of the challenges that you have to deal with when you're working on an HPC environment. The core thing that I would like to convey is that most often it is not really the HPC part that is HPC basically might sound like a intimidating thing, but the ideas behind HPC, these are often very simple and very important. Scalability of system not only is important when you're dealing with a supercomputer, but overall, whenever you're having a data warehouse or developing an application, you need to be able to think about parallelism in general, because that is where we are heading towards. Even the desktop that you're working on, it has multiple cores. So if you're writing an application, are you leveraging the cores that you have? Are you leveraging all the physical threads that you have sitting on your compute cores? And that again goes back to not only the core HPC ideas, but core ideas of computer science, algorithms, networking, operating system, all of these are all important. But if I were to tell you what are the core ideas, core things about scalability and in terms of programming, then languages that I feel are very pertinent and one should know, definitely C, C++, Python, Rust, some functional programming, learn some Racket, completely different way of thinking. Racket is functional programming language. Or learn something even more high level, like a logic programming language, Prolog, Datalog, where you're able to write a Sudoku solver in 3 lines of code, and then let the system work its way. How do you actually compile it to anything else and then run that? But being able to have an abstraction at a very high level, that's a really, really cool ability. In terms of scalability parallelism, what do you have to learn for that? So MPI, this is basically the bread and butter for all HPC people, message passing interface. How do you communicate between compute cores? OpenMP is for threading, and then typical old-fashioned threads is also very powerful. And CUDA. CUDA is something that is very important in able to program a GPU, and GPU is everywhere. Even all these HPC machines, the nodes have GPU. So in addition to MPI of how you move the data between nodes, you need to be able to use CUDA to actually scale the application running on that compute node. And I would like to end this talk with kind of an orthogonal thing. I know it's often very easy to get very engrossed and involved in very core technical courses, but DAIICT actually offers a lot of courses beyond computer science, and I have such amazing memories of those courses, and they really help you get a bigger perspective. And these are really important things. If you were to think, if you were to look at things from a big picture view, I would say. And yeah, so that's all that I have to say, and really thankful for this opportunity. This is my email ID, and I'm also looking for students in general. So I'll be very happy to connect with you. If you want to chat with me, if you want to talk about HPC, talk about these problems that I work on, I'll be very happy to engage with all of you. And thanks again for this opportunity. I really enjoyed. Thank you.
Thank you, Bhaiya. Well, now we would pick up some questions from the audience. So if you guys have any questions, you may raise your hand and we'll unmute you.
Siddharth, this is Suman here.
Hi, Dr. Zuma.
I do not have much interaction with the HPC guys, and I'm not in that area. But I can relate one thing with the data visualization part. I would like to have your opinion on that one, because nowadays people are talking about the digital museum. So there are lots of images, and the visualization of the real objects are being handled by the graphic system and the high performance computing system, so that we can have a visualization of the modern day museum, which we call digital museum. So do you have any comment on that one? How far it is, or what are the challenges in there? Because I know that one of our alumnus, you may be also knowing, Abhishek Kumar. Abhishek was 2008 pass out. Abhishek is working in Apple on this particular idea of image data visualization. So I would like to know your view about that.
No, I think that's a very important question, and so I'll tell you from my experience with working in immersive systems. So immersive visualization is something that is becoming very popular, and there are multiple aspects to it. One is this VR system that you wear, and then the other is augmented system where you have augmented reality, and then the other aspect is where you have panoramic system, visualization system, where you where we actually are inside the system, and that area is actually shared by multiple people. Because if you just have one VR system, that's not really a scalable thing. So all of these are very interesting, and a lot of progress has been made in this area. Like in terms of technical aspects, one of the problems when dealing with VR systems is the frame rates. So you have to have really high frame rates in order to have a really good experience, and that's where it
realistic visualization.
Yeah, and exactly, and then that's where the problem is. You don't really you don't really are able to deal with really large data sets. So being able to create this interactivity is a big challenge. And in terms of deploying this in a museum setting, this is like a really big thing that people are working on, and I feel like we are going to see much more of these, and especially in COVID times, right? And where we want to have this digital experience. Right. Yeah, so definitely. And just to add on to that, like where visualization is heading towards, other thing visualization is heading towards is web-based visualization, like being able to have high performance visualization on the browser using WebGL, leveraging the ability